quiz question. So we got number 4. What is the coefficient in front of AS2O5 right here? So we're looking to balance this equation. We should always look for what's in parentheses first. Is there nitrates, sulfates, things like that? There's hydroxide here, which is a polyatomic ion. There's no hydroxide over here. There's AsO4 here, none over here. So we should do then metals. So we've got 3 calciums here. Let's try a 3 here. If we do 3 calciums there, then let's try to figure out this As, arsenic here. We've got 2 here, and we've got 2 here. Now let's look at hydrogen. You have 2 hydrogens here, and we have 6 hydrogens here. 2 here, 3 times 2. We got 6, 2. It looks like we need a 3 here. Now we got to go to our oxygen. So for oxygen, what do we have? Got 8 here and 3 here. We've got 11 oxygen on this side, huh? What do we got on this side? We've got 3 times 2 here. We've got 6 and 5. Looks like we got 11. That appears to be balanced right there, huh? That appears to be balanced. So what's the coefficient? 1, right? If it's all balanced, there has to be a 1 there. Okay, in number 6, we got sodium sulfide. So let's write this out first. So sodium sulfide is going to be Na plus 1, S minus 2. So that would be Na2S. We have silver nitrate, it looks like. Aqueous solution. So we know they dissolve. AgNO3 plus 1 minus 1. So silver nitrate. Now we get solid silver sulfide. So silver sulfide. So Ag2, it says S, so we know we're going to make that a solid. So silver sulfide, let's make these aqueous. It says they're aqueous. We can put that down. We know sodiums are going to dissolve, are going to be aqueous. We know nitrates are going to be aqueous. And then we get an aqueous solution of sodium nitrate, Na plus 1, NO3 minus 1, aqueous. And we're looking for net ionic out of this. So first of all, let's write out the complete molecular. Na2S 8 plus AgNO3 aqueous. It said we get silver sulfide solid. Plus aqueous sodium nitrate. Then we'd want to balance this. So we've got a nitrate. We'd start with a nitrate, and nitrate on both sides looks good. We've got 2 sodiums here, 1 sodium here. We need to put a 2 here. Now that just changed my nitrate, so I would put a 2 there. And to finish this, you need to split everything up that's aqueous, right? Split everything up that's aqueous, cross out the spectator ions. Cross out the spectator ions. If this doesn't work, put it on the board again Thursday, but hopefully this will work. And then 10. And what are we gonna 10? Okay. So we need the molecular equation. So we need to just write this out, balance it. We've got copper 2 nitrate and sodium hydroxide are mixed. Okay. So let's start with that. Cu plus 2 NO3 negative 1. Can I put aqueous here? Is this going to dissolve? Yes, because it's a nitrate, right? It says it in there, but we know that all nitrates are going to dissolve. We're going to add to that sodium hydroxide. That is aqueous. So this is what we're doing in lab starting today. If you have lab starting today, this is a double replacement reaction where we switch the positives. And if we exchange the positives, because then we can see whether or not the positive ion from this compound is going to come together with the negative ion of this compound and vice versa. So if copper takes the place of sodium, copper plus 2 hydroxide. So we would need 2 there. I'll leave that open. Plus sodium takes the place of copper and NaNO3 plus 1 minus 1. Is this going to be aqueous? Absolutely, 100%, 1000%. Sodium, all sodium compounds are aqueous, nitrates are aqueous. That leaves us with copper 2 hydroxide. Now, I'll gives you, or the textbook gives you those rules. And you're going to explore those in lab today. And otherwise, this is a cheater grid here. And if we look up copper 2 hydroxide, a lot of hydroxides are solids. Here's my hydroxide column, right? Solid, 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 solids. The exceptions are ammonium, sorry, and a few others, but for sure we get a solid here. Now we need to balance this, and to balance this, what do we need to do? I would start with the nitrate right here because we've got 2 nitrates here. So for sure, we're going to start by putting a 2 there. Huh? Now that gives us 2 sodiums, but we should be doing hydroxide next. And with that 2 right there, we're going to want to put a 2 right there. Huh? And then the question is just looking for one of these terms that's here out of everything. Something that matches out of this, out of these 4 terms. Okay. So let's try to see if we finish up today here. We left off on page 11. That looks like this. And it says, does a reaction occur when aqueous solutions of ammonium nitrate and potassium sulfate are combined? So again, this is an OWL question. And OWL gives you the solubility rules And I thought I had him in here somewhere. Thought. Look quick. Yes. So did I pull this from OWL or the textbook? Anybody, does this look like what shows up in OWL? Yeah, okay, so I pulled this from OWL. This is what I'm gonna put on the test. I'm gonna actually give it to you on the test. This exact chart, okay? So again, you'll explore this in lab today, this chart. So let's see what we got here. We've got ammonium nitrate. +1, -1. Now, hopefully I can put aqueous for that. Ammonium compounds are soluble, nitrates are soluble, plus potassium sulfide. And that would be K2S then for potassium sulfide. Aqueous. Yes, all sodium and potassiums, right? All sodium, potassiums, ammoniums. This is aqueous. What are we going to do? We are going to, with double replacement reaction, we are going to switch the positives. So to do that, ammonium is going to take the place of potassium. +1 and -2. So we're going to need 2 ammoniums plus potassium takes the place of ammonium. +1 and O3 -1. Can I put AQ here? Heck yeah. It starts with potassium. AQ. So now you can look back, is ammonium sulfide going to be a solid? So if you look back, we can look at our cheaters grid, but realize the cheaters grid is not going to be on the test, but the same printout from OWL is going to be on there. All right, let's see if I got this. Ammonium sulfide, ammonium sulfide. So mine says that ammonium sulfide is aqueous. So if this is aqueous, we are not going to get a solid. So is there a reaction? No. Now, does my grid match up the OWL problem for this? So I'd have to go back into the rules. Does this match up? Yeah, okay. So we do not get a solid. This ammonium compounds are still aqueous, so everything's aqueous. We don't have to balance it. There's no reaction. Okay, so that completes OWL chapter 3, part 1. And again, a lot of it's going to be in lab this week, looking at precipitate reactions. So let's go on to, this is 3.6, covers acids and bases. Now, what do you know about that so far? You know, we did some acids and we started them with hydrogen, correct? And we had some negative ion to go with it. And you're going to see on the next page, we did naming acids. If you have a base, the generic for a base for sure is XOH. This just stands for a metal. And if you have a base, you have a hydroxide. So we don't do a ton of work in this course with acids and bases. So this does a little bit of an introduction. So Arrhenius definition, an acid is any substance that increases the H plus concentration in aqueous solution. This is my generic for a weak acid. So I could have hydrobromic acid, I could have hydrochloric acid, hydroiodic acid, and then HNO3 would be called nitric acid because NO3 is nitrate, so we'd have nitric acid. So we are going to get a lot of H plus, right? That's what determines how much acid strength we have. So here's an example. This is just hydrochloric acid. So reminder, if we have an acid, it starts with hydrogen. This does not have any oxide in it. So we know that it starts with hydro and ends in ic, right? Hydrochloric acid. Okay, so this is going to give us H plus and Cl minus in solution. So my question to you is, what exactly is an H plus? How many protons, neutrons, and electrons? If we have hydrogen, right here, hydrogen 1, what does it consist of? 1 proton and 1 electron, if it's a neutral hydrogen. No neutrons. 1 proton, 1 electron. If it has a +1 charge, what happened? 0 electrons, right? 0 neutrons, 1 proton. That's all it is. This is simply 1 proton. That's it. So when you see an H plus, all it is a proton. So the next page, hopefully, is stuff we've already done. Well, it is stuff we've already done. Naming common acids. So this does not have any oxide in it, so we know that this is going to start with hydro and end in ic, right? ClO is hypochlorite on our pink sheet, so we get hypochlorous, I to us. ElO2 here minus is chlorite, so I to us again. Perchlorate, I should put it over here. 8, we just changed to ic, right? I to us, I to us. Sulfide. So this does not have oxygen, so we know it is going to start with hydro and end in ic, right? Starts with hydro, end in ic. Sulfite is going to be OUS. And for these sulfur compounds, the weird thing is they keep this UR in there, right? Sulfate is going to be sulfic, and they keep the UR, so we get sulfuric. Nitrite is going to be nitrous for an acid, and nitrate is going to be nitric. So 8 to ic, I to us, if it does not have any oxide, we know that it is going to start with hydro and end in ic. But we did quite a bit of this previously, right? That still makes sense. Okay. Now, here's table 3.1 from your textbook. All right, strong acids. These are strong electrolytes. So what does that mean? They 100% ionize to give ions. Now, you want to memorize these strong acids. There's not very many. Here's how this can help you. So you just got to memorize the Cl, Br, and I for a binary acid. Then here's my rule to remember this if it has oxide. If it has oxide, notice this. You have at least 2 more oxygens than hydrogens. I better put this word in here. Oxygens, hydrogens. Let me zoom in on that. In this case, you've got 2 more oxygen than hydrogen. Here you have 3 more oxygen than hydrogen, and here you have 2 more oxygen than hydrogen, right? That's the way to remember those. Strong acids. What does this mean? All of these are going to split up into ions, 100%. Now, if you have weak acids, what does this mean? You're going to get very few ions. Very few ions. Typically, it's less than 5% split to ions. Notice this is only 1 more oxygen than hydrogen, right? This is only 1 more oxygen than hydrogen. This is more hydrogens than oxygen. There's one being exception to the rule. Oxalic acid. Up here though, nitric, perchloric acid, and sulfuric. Now let's talk about bases. If you have a base, again, typically it is a metal hydroxide. XOH is my generic, a metal hydroxide. Here's my metals: lithium, sodium, potassium, barium, strontium. What's my charge of hydroxide? Always -1, right? Metal hydroxides are bases. Sodium, potassium. On the periodic table, one, right? Lithium, sodium, potassium, group 1. What's the family name for them? Yeah, alkali metals. Then barium and strontium are group 2, right? Alkaline earth metals. Then this right here is ammonia. This is the most common weak base. It is a weak electrolyte, which means you are going to get few ions. I will expand on that in a bit. Few ions. Okay. So 1884, definition of a base. A base is any substance that increases OH minus hydroxide. So these is what your textbook considers. If I put them in for X, these are strong bases. What you get, if it's strong, you get all ions, right? 100% ions here. And the easiest example, sodium hydroxide. Sodium hydroxide, all ions, 100%. All ions. Well, after this, 1884, we go a long ways, and then they have to expand the definition of an acid. And Bronsted-Lowry definition, any acid is any substance that donates, I'm missing, donates H plus proton to another species in aqueous solution. So here's what this looks like. This is my hydrogen. Where did that hydrogen go? Hydrogen had to attach itself to water, right? This does not have a charge. Zero charge. So I am going to expand that out, that definition a little bit, and I'm going to do that right here. Let's look at this real quick here. We have hydrogen. How many electrons does hydrogen have? 1 electron, correct? 1 electron. I'm going to put it as a dot. We're going to do this later on. Now, here's chlorine. Cl. I'm going to put that as an X. We're going to see that it's going to look like this. Each to make this bond, correct? One of each, just HCl. 1 electron from hydrogen, 1 electron from chlorine makes the bond. If we add this to water, I'm going to do X's for my oxygens. Look what happens here. In order to get H3O plus, I need a plus charge here, and I get the plus charge. I say it this way, it's probably not perfect chemistry, but hydrogen leaves its 1 electron behind. If hydrogen leaves its 1 electron behind, my dot right there, correct? That's hydrogen's electron. If it leaves that electron behind, what is it? Just a proton, right? Because it starts out with 1 proton and 1 electron. If it leaves its electron behind, it's just a positive proton. What's that positive proton going to do? It's going to look for a negative charge to bond to. What does it do? It bonds to one of these pairs of electrons right there, either that one or this pair. So let's make a space here and go over. Let's deal with this first. Let's go over here to my right. Here's Cl. Here's the original electrons from chlorine. And then it has hydrogen's electron right there, correct? This is the electron left behind by hydrogen. What should this have for a charge now? -1. How's it getting a -1? It has an extra electron it took from hydrogen, right? This is the extra electron from hydrogen. Now, what's left? Instead of neutral water over here, the water has taken on a proton, right? The water is taken on a proton, and what you'll see is you'll see brackets around this with a charge. For a strong acid, how many of these hydrogens are going to come off? 100%. That's what we mean by a strong acid. 100% turns into ions. %, hydrogens come off. Where do they go? In this case, they attach itself to neutral water. That's how we get the +1 charge. We get the negative charge because hydrogen's electron is left behind. Okay, strong acids. What are they going to produce? H+ or H3O+. Now, the cheater way to do this is just to go H+. I go up here, HCl, aqueous. This is what Al does. Plus aqueous and Cl minus aqueous. Here's what you got to remember. If this is a strong acid, how many ions are you going to get? How many hydrogens are going to split off? 100%, all of them. If you have a weak acid, how many ions are you going to get? Typically less than 5%. You get very few ions for a weak acid. Let's go to the next page here. And to represent that for a weak acid, HF here, weak acid. Right away, for a weak acid, you are going to get very few ions. Now you see reversible arrows. We're going to get, typically, this one's actually kind of high. You get just very few ions. I think this one is 7%. So if you have 100 of these, 93 of these are going to stay attached. The H and the F are going to stay attached. You get about 7% that turn into ions. But you do get a few ions. That is the difference between a strong acid and a weak acid. For a weak acid, you're going to see equilibrium. I'm going to explain that coming up. The reaction goes back and forth, back and forth, back and forth. The H+ comes back off here, reforms the HF and water. And then an H comes off. It just continually goes back and forth. But you get very few ions. Okay, with that, I'm going to back up to a reversible reaction that I said I'd come back to. So that's what I'm going to do. On page, what page was that on? It's like the second or third page. Third page, looks like this. Third page, looks like this. Equilibrium. Let's see what's happening here on this. For this right here on page 3. This is a reversible reaction. The forward reaction here and the reverse reaction here. Now, let's look at how they started this reaction. Since this is a reversible reaction, it goes back and forth. You could start the reaction with reactants, or you can start the reaction with products. If I start this reaction with SO3, what's it going to do? The reverse reaction is going to take place. We're going to get SO2 and O2. If I start the reaction with SO2 plus O2, it's going to start making SO3. In this case, if we look at these lines here, we started the reaction with SO2 and we started the reaction with O2. How much product did we have when we started the reaction? 0. But notice what happens here. SO2 plus O2 makes SO3. This concentration comes up. We're making more and more SO3. As we're making more and more SO3, obviously we're using up SO2 and O2. But look at what happens. It eventually flatlines. When it flatlines, the concentrations do not change. We say that we have reached equilibrium. The concentrations are constant. They do not change. The reaction never stops. In lab this week, all you're going to do is consider reactions that boom, it just goes to completion, done. If you have a reversible reaction, the reaction does not stop. It goes back and forth, back and forth. SO2 combines with O2 to form SO3. SO3 does the reverse reaction, breaks down into SO2 and O2. But the rate equalizes out, so their concentrations remain the same. So if you see equilibrium arrows, the reaction does not go to completion. So that's what happens when you have a weak acid or base. It continually reacts the forward and reverse reaction. That explains these double arrows. The reaction does not stop. Okay. Definition of a base for Bronsted-Lowry expands. A base is any substance that accepts an H plus now. Here is the most common base. This is ammonia. When I see a nitrogen here, and when you see a nitrogen in OWL, this is what happens. Typically, the nitrogen has a pair of electrons that is not bonded. Then we're going to write water as H OH. Just going to write water as H. And I'm going to put the electrons in here. Think of it as HOH, hydrogen hydroxide. Let me zoom in, sorry. Water as HOH instead of H2O. And just look what happens from one side to the other. Instead of NH3, we get NH4 with a plus. What's happening then? Hydrogen comes off from the water, leaves its electron behind. If it comes off, it is only a proton. What does that proton do? It seeks out that pair of electrons right there. So instead of NH3, we get NH4 with a plus charge. We get this negative right here because of hydrogen's electron, right? Here's where we get this negative charge. Now, if it's acting as a base, you better get OH minus. We have reversible arrows here, correct? How many ions are we going to get here? Not very many. We get a few ions. Few ions. This is a weak base. Let me summarize again. If you have a strong acid, how many ions are you going to get? 100%. 100%. What ion do you get? H plus. 100%. If you have a strong base, the strong base is going to be something like this. NaOH that just dissolves into Na plus and OH minus. How many of these are going to split up? 100%. You get a lot of ions, correct? This is a strong base. If you have a weak base, it would look like this. You actually got to have water like this. You get some OH minus. How many of these ions do you get? Just a few. Strong acid, 100% ions. Strong base, 100% ions. Weak acid, few ions. Weak base, few ions. Okay. Again, what are our strong acids? These right here. So it says, write the ionization for HClO4. So there's two ways to do this. We have HClO4, aqueous. Cheater's way to do it is to put a one-way arrow, H plus aqueous and ClO4 minus aqueous. A better way to do it is to do this, HClO4 aqueous plus water, liquid. Know that this is the hydrogen here that comes off. we are going to get H3O plus aqueous and ClO4 minus. This is essentially exactly the same. This is the same thing. H plus in solution is the same as the H3O plus. This is a more accurate way to do it. H3O plus is the hydronium and what has to happen? Hydrogens come off, right? Hydrogens come off, leave their electron behind. Hydrogen comes off, leaves its electron behind. Okay. We say that H2SO4 is a diprotic acid because it has two hydrogens that can ionize, two hydrogens that can come off. H2 diprotic. Phosphoric acid technically would be called triprotic because it can have three hydrogens that can come off. The first ionization is 100%. Let's write that first. The first ionization is 100%. So right here, we'd have H2SO4 aqueous. If we did it the easy way, plus aqueous, and we are going to have HSO4 minus. Otherwise, H2SO4 aqueous plus H2O liquid. %, right? All ions here. Now, realize that this right here still has a hydrogen attached. The second ionization for H2SO4 is it's weak. So we start out with the HSO4 minus. Water. I've got to do reversible reactions now. It's a weak acid. Very few of these hydrogens come off. What am I going to get? I'm going to get H3O plus. Now, what would I have left? I get rid of an H plus here, I'm going to end up with SO4 minus 2. Okay. So 100% of these hydrogens come off. This is sulfuric acid. This is battery acid. If you got here today with an internal combustion engine, battery acid to start it. Okay, the most common weak acid, vinegar, which is acetic acid. There's a couple ways to write this. It can look like this, where this is the ionizing hydrogen. The hydrogen that comes off here, we can put it like this, or you'll see it like this. These are the same hydrogens. These are the same hydrogens. It says, write the ionization reaction for acetic acid. I'm going to do it the way Al does it. They use this hydrogen. So we're going to go CH3, COOH, aqueous. We have an acid. We're going to produce H3O plus. This is a weak acid. We have to have double arrows. Weak acid. CH3COO minus plus H3O plus. Okay, I want to come back to this acid-base stuff, but we need to take a break from acid-base. Let's switch gears. We're going to go forward till we get to oxidation reduction, which is on page 17. And this will help you finish up OWL as well. So we're going to go to page 17. Oxidation reduction reactions. Okay, the Earth's atmosphere contains about 21% molecular oxygen, a chemically reactive gas that plays an essential role in the metabolism of aerobic organisms in many environmental processes that shape the world. The term oxidation was originally used to describe chemical reactions involving oxygen, but its meaning has evolved to refer to a broad and important reaction class known as oxidation reduction, or we just use the term redox. So, oxidation reduction reactions involve the transfer of electrons between reactant species to yield ionic products, such as the reaction between sodium and chlorine to yield sodium chloride or table salt. Now let's look at what's happening here. There is no charge here on this sodium. There is no charge here on the chlorine. Let's review that. If you have sodium with no charge, it is an atom. By definition, an atom, the protons that are positive, the positive protons equal the negative electrons. It's a neutral atom. There is no charge. And how many is that for sodium? How many is that for sodium? 11, right? Sodium atom, 11. Chlorine, neutral atom. Protons equal the electrons. How many? 17. However, when you let them interact and a transfer of electrons takes place, we know we get a sodium ion of +1 and a chloride ion of -1. Sodium ion. We have 11 positive protons. How many negative electrons? 10, right? 10 electrons. We've got a +1 charge. We've got 11 positive protons, 10 negative electrons. Where did the electron go? Well, it went to chlorine, right? Because now it's not chlorine, it is chloride, which has 17 positive protons and 18 electrons now, right? So oxidation reduction is just this. Oxidation reduction or redox reactions are those in which one or more elements involved undergo a change in oxidation number or charge. So for here, sodium undergoes a change and chloride. Now, here's how you make this easy. The word reduction. Things got to get more negative. We're reducing something. Reduction. Which one of these from left to right is getting more negative in charge? Which one from left to right is getting more negative in charge? Chloride, right? This is reduction. The other one is becoming more positive. This is oxidation. Again, go for the reduction. Which one's being reduced? Once you know that, then the other one is oxidation. Then they use these terms. Check this out. So oxidation is the loss of electrons. If you lose electrons, it's going to become more positive. What's undergoing oxidation? Sodium. It's becoming more positive. Reduction, gain of electrons, decrease in oxidation number, it becomes more negative. Then we use the term reducing agent, which is the species that is oxidized, and the oxidizing agent is the species that is reduced. Hauser. Whatever undergoes oxidation then is it's the exact opposite. So this is the reducing agent. And whatever is undergoing reduction. It's the oxidizing agent. So to summarize, if it's an oxidation reduction reaction, the charge changes from reactant to product. The one that becomes more negative is reduction. And then they call that the oxidizing agent. That one that's becoming more positive is undergoing oxidation. And then they call that the reducing agent. Now, we worked on this already figuring out oxidation states or charges. So for a review, what is the oxidation number for sulfur in the following compounds? Hydrogen here is written first. What's the charge of hydrogen? +1. What's the charge of this right here for sulfur? -2, right? This would be hydrogen sulfide. Always look here now at the negative first. What does this Cl have to be? It's chloride, right? What's the charge of chloride? -1, right? If we have two of them, -1, -1, what's the charge of sulfur? +2. This O here automatically is what? This is oxide, right? What's oxide have a charge of? -2. I guess I can write it out like this. NaNaSO. Huh? Oxide -2. -2. -2. What do we have for sodium's charges? Always, always, always for sodium. +1. So we get a +1 and a +1. What's my sulfur charge? +4, right? +1, +1, +4. That gives me a +6 and my -6. So I have a +4 sulfur there. What's my sulfur charge here? +8, right? Oxide's always -2. -8. That had to be +8. What is my sulfur charge here? My 4 oxides here are going to give me -8. My 2 hydrogens here are going to give me +2. +6. +6 on my sulfur, right? All right, we are going to do just a couple down here, some examples. This right here is called a single replacement reaction. This is a single replacement reaction. Single replacement. Magnesium takes a place in nickel. Is this oxidation reduction reaction? Absolutely. How do you know that? You've got magnesium sitting here, has to be a 0 charge. Over here, it's in a compound, it has to have a charge. Nickel here by itself has a 0 charge. Over here, it's in a compound, it has to have a charge. Well, what's my charge of chloride? -1. What's the charge of my magnesium? Always, always, always. +2. My chloride's -1. I have 2 of them. So what's my charge of nickel? +2 for my nickel, +2 for my nickel. Where's reduction? Which one's becoming more negative? Nickel is, right? We are going from +2 to 0 for sure. That's my reduction. That means this is my oxidizing agent. And magnesium here is becoming more positive. So that is oxidation. This is my reducing. Let's do what this is letter D, an oxidation reduction reaction. For sure. How do you know that? You've got iodine uncombined by itself. Iodine uncombined. What is the charge? 0. There is no charge. Over here, it has to have a charge. It's in the compound. So this would be +1 and -1 on this iodine. So we got to figure out, typically it's going to be sulfur here that's changing. Let's see if we can figure out the sulfur here. So we've got, I'm going to go down below here. We've got 2 potassiums, 2 sulfurs, and 3 oxides. So we know we've got a +1, we've got a +1, we've got -2, -2, -2. For the sulfurs. +2 and +2, that work? Yeah, because that would give us +6 and -6, right? +6 and -6. This one, we've got K, we've got S, 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 S. Oh, 2, 3, 4, 5, 6. Wow. Put a -12 up there for those 6 oxides. Potassiums are always +1. +1 and +1, right? That means we got to get 10 out of that. You got to get 10 out of that. So I think Al actually does this. If we take 10 divided by those 4, what do we get? 2.5, don't we? You might say, how in the heck can that be? And it actually is this. One of those sulfurs goes from +2 to +4. That's the only way to get 10. So this one's a little bit goofy. But this for sure is what? This is reduction, correct? Then we know one of these sulfurs is going from 2 to 4, so that's oxidation. Okay, we will finish everything up on Thursday. We'll talk about the test, work in out in part 2. See what you can do with the quiz questions. Try to finish the quiz. Try to finish the quiz. So try to finish this up. We'll answer questions on the quiz. We'll finish it up. We'll talk about the test next time we meet on Thursday.